Welcome to the 13th lecture of class meeting of EECE341, Introduction to Communication Systems. The most important announce is about the midterm exam, which will be held on Wednesday, October 30th, 7 p.m. to 10 p.m. in this classroom. So this schedule is firm, so if you cannot come to the exam, then you have a serious problem. So please let me know. We cannot change the schedule, but please let me know if you have inevitable emergency. Okay, it's an open everything exam except any human interaction. You can use LLM, but that may not be helpful much. The coverage will be up to class meeting 15, which is the next Monday's class meeting. So today, Wednesday, next Monday, class meeting will all be included in the midterm. Homework will be continually uploaded, even though this is the midterm exam period. Here goes the message from me, the instructor. What is the most important message? As an engineering student and science division student, you need to be very versatile in making simplifications and visualizations. Last weekend, one of my son asked me about the math problem appeared in the Korean SAT. And I knew the problem already because it was too hard and it became notoriously famous immediately after its advent. I tried to solve the problem for 6 hours and failed. So this time again, I could not solve. But that is not an issue because I asked him to do what? Simplifications. So divide the problem into easier problems. So given one problem, I asked him to make 5 related problems, which are simpler. And if he could solve it and learn something, that is the progress, even though the problem cannot be solvable in 6 hours. During the simplification, visualization, drawing Venn diagram, drawing a graph, really helps to understand. By doing this, repeating this simplification and visualization procedure, you learn a lot, you experience and you get lessons to become a better problem solver. You may become a better scientist, you may become a better engineer, you may become a better professor. Okay. Here goes the one clarification. After the last class meeting, one of you asked me why I consider linear time invariant channels only so far in this class meeting. And I will give you one simple answer, which is too simple, but the idea is like this. As I told you repeatedly, this course is about communication systems. However, much of the emphasis is on radio communication. What does that mean? Radio communication utilizes radio wave, which is a specific, especially lower frequency range of electromagnetic wave. And in order to generate this radio wave using electrical systems, we not only use circuits, but also use so-called RF circuits and RF components, especially transmit antenna and receive antenna are very important because these antennas convert the wave into electrical signal or electrical signal into wave. Of course, precisely speaking, this transmit antenna converts the radio wave propagating through RF cable to a radio wave that propagates through the medium. And this RX antenna converts the wave propagated through the medium into a radio wave propagating through your RF cable in the receiver. However, we can just assume that these are time functions for simplicity. Now, what is a wave? Radio wave is a part of electromagnetic wave, and electromagnetic wave is a wave. Now, what is a wave? It was very hard for me to understand or even answer the question when I first saw this question from the popular science book. Is light a wave or a particle? And at that time, I didn't have precise definition of a particle and that of a wave. The question itself was very vague. Now, here goes the question, simplified. What is a wave phenomenon? Wave phenomenon can be just said in this way. You have some physical quantity that can be measured and follows a specific differential equation, partial differential equation. So suppose you have some x, which is a function of time and let me use some different thing, which let me just say E and position. And you have a relation between the second order time derivative and second order space derivative with some constant A. Whenever you have a phenomenon or something that can be measured using some measurement equipment, and that satisfies such a form of differential equation, you have a wave. Now, every wave phenomenon have a commonality. What is the commonality? You have what? You have superposition. Principle satisfied. What does that mean? If you have some wave that propagates this way and another wave propagates that way, what is the resultant wave? It's a summation of these two, linear combination of these two, right? So now let me ask you to have a leap of faith. So from here to there, you have a radio wave involved between these two. Now, at the output, with your time function, what would be the output as a transformation of the input? The only answer could be, based on this one, that output is a linear filtered version of input. So we have exclamation, 느낌표, y of t is a linear transform of x of t. Whenever you have a linear transformation, you can apply the shifting property of the delta function to the input signal, and then you use linearity and eventually you will see that your output is a special integration of the input and the response of your linear system to the impulse applied at time tau. So this is a response at time t to the impulse applied at time tau. What does that mean? You have, let me change the order, t tau, x tau, d tau. So this relation between output and input, it governs this radio communication. Output is a linear time varying in general, linear time varying impulse response. Linear time varying impulse response times the input integrated, especially when you have, linear time varying, you have time invariance. Time invariance assumed, then what do you have? This one, ht tau, can be written as ht minus tau 0. What does that mean? Impulse response of the system at time t minus tau to the impulse applied at time t. So using a single response, you can rewrite this way. That is the famous convolution integral. Got it? So as you see here, the result you learned in signal-gen systems is actually a special case of a linear system. That's not all. Remember that, okay? That's not all, but special case. So if you further study wireless communications, especially mobile radio communications, then you will see more often the channel modeled as a linear time varying system. However, this is an introductory course. So as I repeatedly show you in the kind of front page of the class meeting, we simplify the situation. So we assume our channel varies slowly relative to our period of message to be transmitted. Then it can be well approximated by a linear time invariant system. And another one is that if you have an LTI system, then as you see from the shifting property, sometimes you can approximate the impulse response as a weighted sum of delayed Dirac delta functions. So this is the first approximation. And second approximation is what? You have only one path. So you don't have summation, you have a single, some attenuation factor, and some delay. Ready? And so far, I assume the radio channel has single path. So there is only attenuation and delay of the transmitted signal when it is received at the receiver. However, if you kind of do the reverse operation of this simplification, so complexification, then probably we need to go up to this approximation, up to, sorry, let me have one more line. Up to this one. This is the shifting property for the impulse response. And then probably we move up to linear time varying channel. Of course, for the linear time varying channel, we may have something similar to this, and which is one of the most popular approach used in the channel model in radio communication. Anyway, I talked too much. But what I want to say, not fully, but partially, is that the answer is that since radio wave is a wave, got it? Wave has a superposition satisfies superposition principle, which can be well modeled as linear time varying filter. However, for simplicity, we assume linear time invariant system, channel, much simplicity, we sometimes assume the channel gives just us attenuation and delay. I hope you are satisfied. By the way, immediately after we enter into the study of next chapter, angle modulation, in order to motivate why this very good, apparently very good, amplitude modulation and its variants, DSB family and SSB, VSB, has some serious drawback. That's why our engineers, ancestors, devised angle modulations like frequency modulation. Anyway, at that time, I will be back to this channel model again. But so far, just assume that the channel is a linear time invariant channel with a single pass with one attenuation factor and one delay. Okay, here goes the review. So last time we studied SSB and VSB, especially about VSB. My description was very verbal, but today we are going to be very quantitative. So I will derive the most important condition for VSB filter to satisfy. But anyway, the idea was like this. In double sideband modulation, the message M of T is assumed real baseband signal. What does that mean? Real baseband signal satisfies conjugate symmetry in the frequency domain with respect to the zero frequency. Now, if you modulate carrier with that message, what happens? The spectrum of the message converts up to the higher frequency around FC, which is the carrier frequency, and down converts to the negative FC. And let's focus on this positive frequency. What happens? With respect to the carrier frequency, you have upper sideband part and lower sideband part. And interestingly, only when you are given the upper sideband part, you can recover lower sideband part. Not alone with this negative frequency part, because you have conjugate symmetry, right? So apparently you waste the frequency band. You don't need this bandwidth W in the pass band, which is 2 times B of the bandwidth in the baseband. So let's assume in the real baseband, you have bandwidth B, positive B, negative B. From your point of view, it goes up. Then you have 2B in the passband, which is the bandwidth. Possibly you auctioned from the government or you are allocated. Got it? So in that sense, double sideband family has what? Spectral efficiency somewhat half compared to single sideband modulation. And single sideband modulation, unlike double sideband modulation, transmits only the upper sidebands or lower sidebands. Got it? So in that way, single sideband modulation can save the frequency band. So it increases the spectral efficiency. Spectral means the adjective form of spectrum. So frequency. So in the frequency domain, you can save the bandwidth a lot. So you just need half of the bandwidth. In that sense, some people say that DSB has 1/2 of the spectral efficiency of the SSB. Got it? Now, is it just good as the spectrum efficiency increased or doubled? Always something good comes with something bad. One of the reasons why that happens is that the original invention, like DSB, was not the invention by dumbers. Got it? those engineers were very, very smart. So it was somewhat optimized, practically optimized system or scheme at their age. But as the technology evolves, especially this left side building electrical engineers and scientists pushes up the human boundary, right? And new technology allows these right side building guys to devise a better idea. So, for example, designing a bandpass filter with very sharp cutoff was not possible, for example, in the invention of the DSP. However, after 10 years, these filter design guys started to design very sharp cutoff bandpass filters, something like that. So previously impractical idea becomes practical as the technology evolves. That is the idea of SSB. So SSB requires much difficult filter design if we just use what? Sideband filter based implementation. So still, even though the technology evolved, probably these engineers in left side building of electric engineering complained to this right side building engineers. Hey, even though we improved a lot, still it's complicated. Is there any other idea? So what do? They do is like this. So you have some mathematical formula. And interestingly, you can find some other representation of the same thing. For example, you have real valued bandpass signal x of t that can be written in the form of what? In phase plus quadrature components. Or you can rewrite it as what? Amplitude times cosine 2 pi fct plus time varying phase deviation theta of t. And you may say that they are equal. What's the point of that? But this different representation or description gives us a lot of insight. One is that the in-phase quadrature representation allows us to think in that way. Okay, in order to make a modulated signal, we may start from a DSB modulation for in-phase part. So we have x sub I of t times cosine 2 pi fct plus constant theta. And we also have DSB modulation, xq of t times now sine 2 pi fct plus theta. And we subtract. And we have a single bandpass filter. And that is a way to generate a real valued bandpass signal. Or we may devise something called voltage controlled oscillator. So we generate amplitude signal and we generate phase deviation signal. Now this phase deviation signal goes into the voltage controlled oscillator and then it generates some constant envelope signal but time varying phase, and you use what? Mixer to multiply these two. And interestingly, you have the same signal. So what was the idea of this one? The idea was like this. Upper sideband SSB signal can be generated in this way. You have a message and you have the Hilbert transform of the signal. Now, what do? As I just told you, you use IQ modulator or phase shift modulator, which the in-phase part accepts message signal, quadrat phase part accepts Hilbert transform version of the message signal, and then it modulates with cosine. It modulates cosine and negative sign, and the sum becomes upper sideband SSB signal. It's amazing, right? So please remember this. Given a mathematical formula, it may have different form, but all equivalent. Interestingly, each representation may give you a different idea to implement this one using circuits. Got it? That is the idea. So it's not like this. As a high school student, 3 years, 4 years ago, you are given a very difficult problem. And your friends try to solve that problem in that way, the other way, and you solved in some way. And your teachers pets you and say that, great, you solved it. So how did you solve? I used this method. Very creative. What about seeing this so-called standard solution? And you may say that, no, it's okay. I just solved it in a creative way. I don't need to read it. I don't be affected by other person's solution, which may demolish my creativity. Don't do that, okay? Because same answer with different form of representation is the key to have a breakthrough or to have a new invention. So if some of your friend gives you different solution, even though the answer is the same, ask him or her, show me. I really want to see a different way of to do this. Got it? So please remember this. Anyway, for the lower sideband SSB, what do you need to do? You just need to change that sign, right? So in the transmitter, by implementing a Hilbert transformer, we may generate single sideband or double sideband, single upper sideband or lower sideband SSB signal. The problem is that still this Hilbert transform is very strange LTI filtering with impulse response that is non-causal and that is not bistable, right? As you can visualize this impulse response, it's a real valued impulse response, but looks like in the time axis this way. So it's not causal and it's not absolutely integrable, which means very bad impulse response it has. However, by delaying the impulse response and approximating this infinite support of the function, you can well approximate the Hilbert transformer compared to the impossibly sharp upper low pass filter or high pass filter that are required in sideband filtering implementation. Got it? So always think about this way. Hey, this mathematical formula directly implemented line by line, term by term, factor by factor, is it implementationally expensive or inexpensive? You have different formula, different looking formula equivalent, and you just think about term by term, factor by factor, and see, A, is it easy to implement? Sometimes just simple change gives you a lot of advantage in implementation. Got it? So please remember that. Anyway, so in the receiver, what can we do? The idea is this. If we have coherent demodulator somehow, so we have a received signal, and the difference is that you have two terms in the real passband signal, which has fixed phase deviation, because in the SSB, you have always in phase and quadrature components. They are not totally unrelated, but they are quite different, right? They don't have common amplitude. One has M of t, the other has the Hilbert transform of M of t. So they are not the same. So you have in phase and you have a quadrature. From that, how can you exactly extract the 2 pi FCT plus data? It's more difficult than in the DSB receiver. But anyway, for simplicity, right? For simplicity, let's assume coherent demodulation is possible. What does that mean? Demodulation carrier has no frequency offset, no phase offset from the received signal. Right? Then what will happen? You can simply use the same structure as that of the DSB coherent demodulator. You can recover the message. Why? Let's think about the upper sideband SSB. Now you right shift and left shift and low pass filter. What happens? Here in the baseband, you have the positive sideband, you have the negative sideband put together and become a signal, just a simply scaled version of message. Done, right? So it's amazingly good. The problem is that as we resorted to the envelope detection in the DSB demodulation, it's not easy to have perfect phase coherence or phase synchronization of the carrier, demodulation carrier to the received signal. So we have some phase difference. It may be slowly varying, it may be almost fixed, or it may be fast varying due to possibly carrier frequency offset. In that case, you have very severe distortion at the approximate coherent demodulator. Okay? So that's not good. So they also have an invention. As you've seen in some of the homework problems, for the SSB, you can put in the transmitter a small carrier or large carrier. It's possible, even though our textbook and most of the textbooks do not introduce that one because they do not want to ward off you from just taking this AM part. But that kind of idea was also invented. However, one of the very interesting idea, which is included in our textbook, is so-called carrier reinsertion at the receiver. Okay, so at the receiver, we reinsert the carrier. The unfortunate part of our textbook, and most of the textbook, is that when they reinsert the carrier in the receiver, they assume that for simplicity, the inserted carrier has same carrier frequency and phase deviation, so that their derivation is simple. However, as I told you, you can show that even though reinserted carrier has phase deviation from the received signal, still the carrier reinsertion part followed by envelope detector gives you correctly demodulated message signal. And I asked you to do it yourself. Got it? So here goes the kind of summary of the SSB. It has some pros and it still has some cons. What is the most important pros compared to the DSB family? Spectral efficiency. You can save the bandwidth. What are the problems caused? Computational complexity, computational implementational difficulty. Got it? So it's a kind of trade-off. So initially AM became popularized for radio broadcasting. Everybody wanted to have a radio set. For example, if you have a baseball fan, probably you've seen some old photos. They broadcast World Series baseball around the United States in the early time of the AM radio broadcast. Many people gathered to the radio receiver to see some legendary baseball pitchers or hitters do something. Got it? The problem is that the people wanted to see the image, not just listen to the voice of the pastor. They wanted to transmit image, video through air by using radio wave. And the difference is that even though I didn't explain at that time, the voice has very small bandwidth in the baseband. However, in order to transmit video image, you needed more bandwidth. And the CRT at the time had some property. That signal, that analog signal for analog TV, had significant DC component or component around DC. So SSB damages the signal a lot. So they wanted to compromise SSB and DSB. That is the idea of VSB. Here V means vestigial, which is the adjective form of vestige. I believe. In Korean, 흔적, like in 흔적기관. So something is remained. Actually, the other side of sideband. So if you are interested in upper sideband, then some part of lower sideband is also transmitted. That is the idea of VSB. So today, I'm going to derive that one. Here. So let's think in the frequency domain. As I told you, in this textbook, linear modulation means what? DSB or DSB family, possibly filtered in the real bandpass, real passband. If you have modulated signal that can be rewritten in that way, you have a linear modulation. So let's start from DSB. So here you have FC and negative FC and some message here. For simplicity, I draw as if the message is real valued positive Fourier transform, but actually it is not, right? As you know, you have what? Conjugate symmetry of these two upper side, lower side with respect to FC and conjugate symmetry. And also this positive frequency and negative frequency components has conjugate symmetry. Right? Now, given that, you build some filter, real valued bandpass filter. Something like this. Let's say this filter has frequency response capital G of F. And since we are assuming real valued bandpass filtering, this filter also satisfies conjugate symmetry. Right? So that's why I emphasize again and again and again and again in the beginning of this course. When you review the signal gen systems part, in this course, one of the most important results is what? A real valued bandpass signal has its Fourier transform that has conjugate symmetry. So you have that part too, right? Otherwise, if you don't have conjugate symmetrical part here, your filter does not have a real valued impulse response. So you have this situation. So the transmitted signal, let's say X tilde is X of F, G of F multiplied. X of F is DSB. This is DSB signal, double sideband signal, and this is real bandpass filter. To do something, for example, suppose you have some filter like this. What does this filter do? It preserves upper sideband part of the DSB signal, but cuts out some part of the lower sideband, right? And now let me ask you, if that is transmitted and received with a single attenuation factor and delay components, then can you recover the message? Ideally. Of course, yes, because you just received the signal, you cut off the entire lower sideband, and then you use coherent demodulator, then you are done, right? So in that way, mathematically speaking, so in terms of this right side building electrical engineers terminology, this signal contains the message signal, and you can perfectly recover the message signal. Now, what about you have some distortion from this sharp filter? For example, you have something like this. So you find you have some point of symmetry, and you have a slope here, and you have flat part. What if your bandpass filter has filter response like that? And let's see what will happen in the coherent demodulator. So you have x tilde of f, x tilde of t. Just for simplicity, your received signal is assumed to be the same as the transmitted signal. You have here cosine 2 pi fct plus theta. Okay, let's assume theta is 0 for simplicity again, okay? And you have ideal low-pass filter. What will happen? So let's see here at this point. So this is, let me say, this is y. And let's say this is z of t. So z of t equals what? X tilde of t cosine 2 pi fct. So in the frequency domain, what do you have? You have right shift and left shifted versions summed and divided by 2 at here. Now, what about using x tilde of f equals m of f minus fc plus m of f plus fc, possibly divided by 2, but let's forget about it. Here, what will happen? And also, let's assume that g of f, let me use g tilde here for simplicity. Okay, yeah. And g tilde is also some g of f minus fc plus g of f plus fc. Here, be careful. G of f is not conjugate symmetric. But it's still okay, right? It's a bandpass signal. M of f satisfies conjugate symmetry. This is our assumption, right? See that? Since we have asymmetry with respect to f equals fc, so if this is the response f tilde, g of f cannot be real, right? As you know. Now, we substitute here and try to find low-pass filtered version of g of f. Then, interestingly, we have what? We have m over f, g of f, plus m of, let me see. M of f Just a second. Yeah, just a second. M of F. G of negative F. Really. Something like this. If I remember correctly. So when do we have this equals M of F? If you factor this out, what do you have? You have G of F plus G of negative F divided by 2 in this case equals 1 for all F within the frequency band of the message signal. So let's see. Suppose you have, let me see. You have some G of F, which is complex valued in general, has some form like this. Then what does this mean? This is the symmetrical part of this signal. What does that mean? You flip this one and add and divide by 2. What happens? If you flip, then you have this signal, and you sum up, then you have flat signal. Now you divide by 2. What does that mean? Effectively, this sum gives you ideal low-pass filter response. Got it? Let me check again. Is it correct? Let me see. Just a second. Yeah, I believe I'm correct. Am I? Just a second. There should be conjugation. Just a second. Just a second. So G tilde of t equals real part of G of t to the j by epsilon. So we have half G of t e to the j by epsilon t plus conjugate t to the negative j by epsilon t. So I have a Fourier transform which equals f G of f minus fc plus. So what is the Fourier transform of G conjugate of t, whether G is real or complex valued? You have conjugation and negation. So you have G of conjugate negative f minus fc, I believe. So I believe we need conjugation here. So this is the requirement. Got it? One of the reasons why this simplified version worked is that I assumed the real value, so no conjugation required. But according to the derivation for general complex valued G of t, we need conjugation. So this is the necessary and sufficient condition for VSV bandpass filter in the transmitter to satisfy for perfect reconstruction at the receiver with a structure the same as DSB SC coherent demodulator. Got it? So the people at their time adopted such a filter like this. Right? So you have the entire B to W bandwidth for the DSP, but you taper this part. And usually they applied linear shape for their VSB filter and flat, but that is a kind of sufficient condition. It does not need to be a linear function. Got it? As far as it satisfies conjugate point symmetry with respect to your carrier frequency in the passband, it works. Got it? So some of you may find this approach may look complicated, but you must be very good at it because this is the core. This is the fundamental skill you need to learn through this introduction to communications systems. This trick, this tool, this mathematical tool to convert the real valued bandpass signal or real valued bandpass signal to equivalent real complex baseband signal with some complex exponential carrier. This trick is very, very important and come again and again and again through your study of radio communication. Anyway, so VSB now has spectral efficiency greater than DSP, but in general, less than the SSB, because SSB transmits only one sideband, but VSB, as the name says, has some vestige in the other sideband. Got it? But it has something good. What? It's more computationally or implementationally simple compared to SSB receiver. That's why the NTSC, that is a standardized TV broadcasting method, especially in the United States and Canada and in Japan and Korea, long ago, before 1980 something, 2 or 5, I quite do not remember the exact date, for the black and white transmission, and later its advanced version to transmit color TV, which adopted this modulation, VSB. Got it? Cone's still spectral efficiency is lower than SSB. Implementational complexity or cost higher than DSP. So this VSB is a kind of trade-off between DSB and SSB. But it was good for TV broadcasting. That's why it is adopted. And interestingly, even though now our digital TV broadcasting does not necessarily require VSB, but still they have these TV broadcasting guys, engineers devise the VSB-like digital modulation scheme. And that is quite interesting. Okay, so I have covered this part. By the way, what about the envelope detection of VSB signal? Can you do that? Yes. One of the simple way is this one. When you transmit VSB signal, you have what? You have VSB with transmitted carrier, for example. Then what happens? If you left shift and right shift the received signal in the receiver, what will happen? Not only this part will combine together, these carriers will combine together, and what? Your received signal becomes almost the same as the intermediate signal in the DSB demodulator, right? So you can use envelope detector to extract the message signal. Right? So very good. And also this carrier helps for the receiver to manually adjust its signal. So you don't know, you never saw analog TV receiver, but I did a lot. And it has some dial so that you can slightly change the nominal carrier of your channel, TV channel. So it's like, I still remember when I was 7 or 8, my sister says, hey, brother, adjust that. And then I go to the TV set and adjust it until we have a clear video image, something like that. Okay, this is the review and some parts of the preview. Now, these are the topics to be covered in this week and probably up to some minutes of next Monday. So my target is to finish up chapter 3 and include all the material of chapter 3 in the midterm exam. So let's see. Here goes the slide entitled Mixing. And as I told you, in a week or two, mixer or mixing has different meaning in radio communication and in audio or speech or acoustic signal recording. So your musician friend who utilize electronic, some gadgets, he or she has different idea about mixing. So as I told you, some people believe mixer is a multiplier. Some people believe mixer is an adder, okay? However, in our case, we usually use term RF mixer in order to reduce the confusion, okay? And RF mixer does what? Not only multiplies two signals, but also one of the signals is usually, not always, it's usually an unmodulated carrier. So you have here a mixer, right? It has two inputs. And now see that here, what is this one? This is unmodulated carrier. See that amplitude is fixed. Frequency, even though this is plus or minus, but fixed, right? So this is unmodulated carrier. And you have here amplitude modulated signal, right? So a mixer usually has two inputs, of which one is unmodulated carrier, right? So this is an RF mixer. And RF mixer does what? Multiplication in the time domain of two time functions. And you may say that, okay, what's the deal of multiplication? But as I told you, multiplication, probably you learned according to your standard curriculum, you learned in the second grade elementary school, not the first grade. Because what? Addition is learned in the first grade, and then you learned multiplication. Multiplication requires 8 years of intelligence of human being, okay? I believe no monkeys and no pigeons can compute multiplication, cannot understand multiplication. So multiplication requires intelligence, huge intelligence, even though it seems too easy at your age, but it requires a lot. I believe in our galaxy, our Milky Way galaxy, there will be only a few aliens who can compute multiplication, I believe, okay? And just think about the history of Earth. Can you believe that the velociraptors can compute the 2 times 2? I don't think so. So even though there are some aliens that definitely they cannot compute multiplication. Now, what do we do, human beings? We kind of build inanimate, lifeless materials to do the computation, like multiplication. Isn't it amazing, right? So, as I once told you, suppose you have so-called OP amp. What does that mean by OP? Operational. Then what is operation? Plus, minus, multiply, divide, integrate, and those so-called mathematical operations. So this amplifier can help, as far as this is invented, can help us to build a circuit that has some intelligence, right? And this allows us addition and inversion of the signal, which means that you allow x of t plus y of t. It allows, given x, you can generate negative x, of course, subtraction. Of course, amplification, scaling. What does that mean? You can do something like this. And in addition, you can do integration. You can do differentiation. Hey, think about that. Your elementary school cousin, second grade, fifth grade, has no idea about differentiation. And your circuit can do that. Isn't it amazing? So anyway, so we can do this. Interestingly, there are some companies who produces very good, very, very accurate RF mixers. And they kind of, how to say it, they have the 90% of the market penetration or something in the world, okay? So, for example, if you are really interested in circuits, but you want to play in this radio communication market, what about becoming an RF circuit or RF component designer? For example, you design RF amplifier, very, very powerful, very small, very power efficient, emitting less heat, right? Something like that. And also RF mixer that mixes signal very, very accurately with very small delay or something like that, okay? Usually, these RF mixers are passive components, but as I corrected last time, there are active RF mixers too, right? Here, passive means that you don't need to apply supply voltage. In the old terms, 밥을 준다라고 하죠, 서킷에. One of the interesting discovery when I came to postdoc is that no student knows the term 서킷에 밥을 주다. Nobody knows. And it turned out that the postdoc was established in 1987, and most of the professors came from the United States after they getting the PhD and has a long period of working experience in companies and universities. And when they started circuits lab, they didn't use that jargon. But when I became a sophomore in electrical engineering, every TA said, "Hey, Junho, you forgot to circuit에 밥 주는 것." That kind of thing. Anyway, so passive means no pop, no supply voltage. Active means that it consumes, it has supply voltage and consumes the extra energy or power. Got it? So passive mixer has only 3 terminals, really 3 terminals. You have SMA connectors, for example. Here, SMA is one of the connector type for RF cables. Anyway, so something like this here, in 1, in 2, out. So in the cover, off-the-shelf. This is an off-the-shelf RF mixer, passive RF mixer. And it really has 3 terminals. And each terminal actually has what? Enables the connection to a coaxial cable. And each coaxial cable has ground and signal. So you have 2 port, 2 port, 2 port. Got it? And here goes the input 1. Here goes input 2. As here, input 1, input 2, and output. Got it? So if you have a passive mixer, it looks like that. If it is an off-the-shelf RF mixer. Of course, in the RF circuit, it becomes very, very small. Okay, that size is around this one, very bulky, but it's okay for prototyping in the research lab. So usually professors use. Anyway, so this is an RF mixer. And RF mixer does, as I told you, what? Computation. So in the time domain, multiplication of 2 time signals, 2 time functions, and generates a single time function. It's amazing, right? Of course, it has, as I told you, limitation. Because they usually, in the RF mixer, assumes that one of the signal is what? Is an unmodulated carrier. They utilize, exploit that constraint or condition. So they somehow put some nonlinearity and filtering in order to suppress the harmonic components. But at the output, it looks like almost perfect time domain multiplication is done in the time domain. Now, in the frequency domain, what do you have? Assuming one of the input is an unmodulated carrier. It does what? It does frequency domain up conversion and down conversion. So here goes the terminology. Up conversion and down conversion. So let's see. Suppose you have some x of t, and here you have cosine 2 pi fct. Then what is y of f? As you know, you have up converted version term plus down converted term, right? So this first term is what? X of f, right shifted by fc. The second term is f of x of f, left shifted, down shifted, okay, in the frequency domain. So this up converted version of x of f, and this is down converted. Down means frequency reduces. And you may say that, hey, I already know this, but you need to know something more. The problem is this. The problem is that even though in the, for example, DSB transmitter, let's think about AM radio broadcasting. I asked you to remember this one, right? So in Korea and United States, 535 to 1605 kilohertz is the radio frequency band utilized for AM radio broadcasting. And this is 1.6 megahertz, right? Approximately. What does that mean? In a second, your oscillator has 1.6 million cycles. It's amazing, right? Very, very fast. And in the early stage of radio communication, high frequency local oscillator, do you think was it easy to build? high frequency local oscillator with very accurate frequency. Does it look like easy to build? Probably not, right? Usually, if you have some extreme engineering, it's hard to build initially. So what do? The idea was simple. Okay, this could be, let me see, can we do this? Something like that. Right? So it's the idea of divide. Once I told you, interestingly, great inventions are based on plus, minus, multiply, and divide, and something like that. Of course, they also have an idea to convert the scarce resource to an abundant resource. So if you generate 1.6 megahertz immediately, directly, that is difficult. What about divide it into two with a lower frequency and another lower frequency? So here goes the idea. What about you have two local oscillators with lower frequency than your target, but you use two RF mixes? So it's like one local oscillator, very expensive, but two local oscillators with lower frequency is not expensive. And RF mixer is not expensive. What would be the immediate idea, right? Divide, multiply, you double the number of mixers, you double the number of local oscillators. That would be the idea, right? So there goes the idea of heterodyning. Okay? Here, hetero means different kinds. Okay? Here, dyning means just interpreted as mixing. Okay? So heterodyning means that you multiply two signals with two different center frequencies. Okay? That is the idea. And it seems time's up almost. Okay, it seems I have 2 more minutes. That clock is something long. So let me talk 2 more minutes. So heterodyning is the idea. So your target frequency is too high with a single local oscillator and single RF mix. So what you do is that you have 2 local oscillators, 2 mixers. What about 3 local oscillators, right? It's like when you count 1, 2, and many, right? So if you can move from 1 to 2, then what about 1 to 3 or 1 to 4 or 5, 6, 7, right? So theoretically speaking, heterodyne transmitter or receiver, if you want, may have multiple local oscillators and multiple RF mixes, as you wish, right? If you want. That is a way. Of course, whenever you have some many components, your implementation error accumulates, so you need some idea to suppress that. But anyway, that is the idea. Then what is this super? So super is a kind of prefix to this heterodyning or heterodyne transmitter or receiver. And this super is something better, something good. You just understand that way, something more clever, okay? So next time, you need to know what happens in the super heterodyning and what kind of something more is done super heterodyne receiver compared to just the heterodyne receiver. Got it? Okay, that's all for the day.